For those who have never witnessed the process of basic steel making, get ready for some pretty dynamic views from Wheeling Pittsburgh Steel Corporation. It's an awesome operation in terms of size, yet highly intricate in the pinpoint coordination of people, materials, and processes. For all its overwhelming magnitude, the process of steel making can be likened to a stringently choreographed ballet, where every step of the dancers must be in sync. We are pleased to give you an inside look at exactly how we make steel happen every day. Welcome to the number 5 blast furnace at the Steubenville South plant. This is the starting point for our look at how more than 3,000 Wheeling Pittsburgh employees make some of the best steel in the world. As you can see and almost feel, people and hot metal get pretty close to each other. Working safely and being safety alert is always part of each employee's workday. 2,600 degree Fahrenheit molten iron falls into giant containers called bottles for transport to the basic oxygen furnace. At the basic oxygen furnace, or BOF as it is called, this iron will become steel. This business takes a lot of muscle. That much is unchanged in hundreds of years of iron and steel making. This plant covers hundreds of acres in Ohio and West Virginia on both sides of the Ohio River. A network of pipes, railroad tracks, and an unseen network of computer cables connects everything. Significant computerization gives Wheeling Pittsburgh Steel the precise control necessary to make steel to the most exacting standard ever imagined, with a workforce that cares about the quality of steel. It's this combination of high technology equipment and skilled labor and management, all working together in a cooperative partnership, that makes the big difference. Today, there is a realization that everything is intertwined. Just making steel isn't enough. Listen to Tom Helinski, General Manager, Primary Operations.
Making steel revolves around what our customers want. After a customer places an order for a particular type of steel, we need to know quantity, width, thickness, and when the customer wants to receive it. The first part is handled by the commercial, sales and production planning group. Once these details are made known through the computer system, the actual melting of steel happens. Molten iron comes from the blast furnace. It's transported to the steelmaking shop. Hot metal, scrap up to about 25% of recycled steel, and alloys are mixed and reacted with oxygen to produce the steel. Then slabs are produced and rolled to customer specifications. All this requires the safe, environmentally aware teamwork of each employee to assure the customers get the quality product they want.
We've honed our company and Steubenville Works into a cleaner, sharper organization in the past few years. We reflect the new demands of the marketplace. We're big enough to have the equipment, resources, and expertise to be aggressive and competitive, yet we're small enough to provide the fast turnaround and quick response that our customers need. We've invested millions of dollars in equipment and research and development to stay on top of the steel-making process. When we trim a ladle of steel to metallurgical specifications, the customer is assured of getting exactly the steel ordered. Our attention to detail exists at every step in the process. Our customers appreciate the fact that they get exactly what they pay for. In a global world, our customers want us to be the best source of steel. We want them to be the best at their business.
Our people are very aware of the competitive nature of the steel business and the need to compete in this arena with a consistent, high-quality product. Not only have we committed resources to new equipment and technology, but we have also strived to heighten employee awareness of their individual commitment and contribution to quality. competitors who survived the decade of the 90s must have an attitude which builds quality and continuous improvement into every pound of steel that we produce.
In the next few minutes, you'll meet many people in the Wheeling-Pittsburgh family as we take you on a trip through the entire process of steel making in Steubenville. Ever since iron masters in the 18th century learned how to make coke, coal has been a critical ingredient in iron and steel making, and there is certainly a lot of coal near this river. In fact, for more than 100 years, this spot on the Ohio has been used for iron making. The coke batteries are on the West Virginia side of the river at Follinsby. Of course, the coke ovens in our 4 massive coke batteries are a bit larger than back then. Special mixtures of high-grade metallurgical coal are loaded into the chambers called coke ovens. Heated in the absence of air, the coal becomes coke, which is almost all carbon. This is a process called destructive distillation. Consider that if the coal was heated with air present, it would become ash and be of little value to Wheeling-Pittsburgh steel. There are byproducts, too, which we use in many ways. Coke gas heats the coke ovens and provides basic fuel for the other operations around the steel plant. Other byproducts are sold to chemical companies and end up as everything from cleaning fluids to pharmaceuticals.
Although the need for coke has existed for hundreds of years, coke-making technology has not drastically changed. We make coke today much like it has been in the early part of this century. The aspect of coke making that has changed are the environmental constraints placed on us by federal, state, and local environmental agencies. The days of needing headlights at noon and reports of rivers burning from the oil on them are gone. Today's environmental laws require us to virtually eliminate emissions from all potential leak points on our coke ovens, utilize state-of-the-art bag houses and scrubber systems to capture fugitive emissions from the coke pushing process, the sulfurization of coke oven gas that is used as a fuel in the steelmaking process, cleaning of wastewater and stormwater to a quality as good as existing river water, and the sweeping of paved roads and applying of dust suppressant to unpaved roads to minimize airborne dust. Tens of millions of dollars and countless man-hours have been spent to accomplish this monumental task. Our employees have made environmental compliance as important as safety and production in completing their daily work assignments.
Automated trains bring the coke and iron ore to the blast furnaces. It is here that the raw materials are melted down, refined into iron. In its most basic sense, iron making hasn't changed in hundreds of years. Men still must prepare the pathways to take the iron in one direction, the slag or waste products in another.
Quality iron provided to the BOF for conversion into steel is the purpose of the blast furnace. The iron making process itself is rather complex and involves a multitude of thermal and chemical reactions. Predetermined measured quantities of iron-bearing materials, coke and dolomite, are taken and charged into the furnace where the iron-making process begins. Essentially, the process requires an extraordinary amount of heat or energy to produce iron from the charged materials. This energy source is mainly provided by coke, which is a carbon-bearing material. Preheated air is introduced into the base of the furnace, where oxygen in the air combines with carbon in the coke to provide energy and reduce gases, which in turn extract iron from the pellets. Many impurities in the raw materials are removed by charging dolomite, which acts as a flux. These impurities are removed in the form of slag in order to provide the BOF with quality iron. Sampling of the final product is performed to assure that the iron is within our quality specifications.
There are numerous examples of Wheeling-Pittsburgh Steel's ongoing commitment to maintaining modern facilities. For instance, the rebuilding of the No. 5 blast furnace at the Southworks, a $54 million effort, was a massive undertaking. The investment significantly increased the furnace's iron-making capacity, ensured that the molten iron's quality is among the best in the industry, and provided additional safeguards to further protect the environment. With the advent of process control and automation at the blast furnace, Better control over the operation and iron-making process can be achieved. Efficiency is provided through the gathering, availability, and use of information on the various facets of the operation. Automation of stoves, which provides the energy and heat for the preheated air for the furnace, is a prime example of how process control, automation, and information through instrumentation can increase the efficiency of the process. By increasing control and knowledge, and by reducing the manual operation of equipment, a gain in hot blast is achieved, which in turn increases the efficiency of the blast furnace. The same can be said for any portion of the operation. The stockhouse, where raw materials are gathered, weighed, and charged into the furnace, can be automated. The cast floor can be rearranged to decrease the labor-intensive casting cleanup portion of iron making by instituting automated equipment for iron and slag handling. And the charging system can be improved so that raw materials will be distributed into the furnace as efficiently as possible.
All of the aforementioned increase the efficiency, productivity, and control of the furnace and the iron produced.
In fact, we operate a phenomenal number of specialty repair and maintenance shops to keep all of this rolling stock and steel-making equipment in business. We can't call a handyman when something isn't exactly up to specs. Electric motors, small and large, are repaired and rebuilt here. We are self-sufficient because of the need to respond quickly to the day-to-day maintenance activities. This is a 24-hour-a-day, 7-day-a-week business. Think of the BOF as a lot like Mom making a cake from scratch. Flour, butter, and other ingredients go into the mixing bowl. Well, you get the idea. Here, the mixing bowl is a gigantic furnace capable of holding 300 tons. And what we mix are iron, scrap steel, lime, lots of oxygen, and a variety of other alloys. We add the ingredients to the furnace in a process we call charging. We call the mixture itself a heat. The charge consists basically of about 250 tons of iron and 90 to 100 tons of scrap because steel is a recyclable material, yielding 293 tons of liquid steel. Think of it this way. An automobile may have 1 ton of steel in it. That means that every 55 minutes, Wheeling, Pittsburgh is making the equivalent, steel-wise, of about 300 automobiles. The process takes about 19 minutes. What makes it all happen in just 19 minutes is the oxygen used to refine the iron into steel. The oxygen is introduced through a water-cooled lance about a foot in diameter. Nearly 22,000 cubic feet of oxygen a minute are used. The fluxing materials are loaded in from overhead bins after the oxygen blow begins. During this period, the temperature rises to 3,000 degrees as the refining takes place. The fumes are drawn off and cleaned through Venturi scrubbers to reach acceptable environmental levels. During the melting or blowing process, the impurities from the iron are burned off and transmitted into the slag and waste gases. This refining process takes about 20 minutes. Then the furnace is rotated so that the heat of the steel can be tested for temperature and chemistry. If all is satisfactory, we will tap the heat and send it to the continuous caster. On its way to the caster, the steel stops at the ladle metallurgy facility. Here, the exact chemistry of the steel is set. The temperature is brought to exactly the right level. These are 2 critical steps to ensure quality and precision. Among our innovations is the use of argon to stir the steel for temperature homogenization as well as for steel cleanliness. In a lab adjacent to the ladle metallurgy facility, we check the quality at our modern facilities. The continuous caster takes our 293 tons of 3,000 degree Fahrenheit liquid steel and turns it into a solid slab of steel in one smooth, non-stop motion. a problem that had baffled steelmakers for 100 years. It's the incredible temperature, of course, which makes this such a complicated process. Imagine the special materials we need to use in all of this equipment so it doesn't melt down. We call the insulating material refractories, and there's a lot of it here. For example, the lathe will dump liquid steel through a trough. We call it a tundish. The tundish is lined with special materials. The steel goes straight down into the molds that begin to create steel slabs. The molds are water-cooled. This brings the temperature on the surface of the steel down, low enough to make it harden into a shell. More than 10,000 liters of water per minute are used to do this. Of course, the inside of the strand is still molten. The molds force the steel to make a 90-degree turn. By this point, the steel is about 1,500 degrees in temperature. Computers monitor every aspect of this operation.
We use several computer systems to monitor and control our state-of-the-art operation. There are computers that enable us to change our slab dimensions while running, others that monitor casting speeds, temperatures, and grades, one that adjusts water cooling flow rates, and other computers that interface the entire operation. The caster is managed from this control room called a pulpit that overlooks the equipment.
On this display here, it shows the mold. That's the upper part. It has the different segments in the machine itself. And this is a graphic display of what's going on outside and in the machine. It tells me the casting speed. It tells me how many tons are in a tundish. It tells me the temperature of the water going inside the mold versus the temperature going out of the mold. And if there's an alarm, it will turn red and an alarm will come off on our panel. And I have to make the necessary adjustments, notify the right people, depending on the severity of the alarm.
Close monitoring of the process is a must. The temperatures put severe pressure on the equipment. For example, the refractories lining the tundish are 12 inches thick. Yet after about 8 ladles of liquid steel, the tundish is changed so that the linings can be replaced.
About 1/3 of the cost of converting liquid steel to slabs is tied up in the refractory materials that directly contact the steel. As the safety and life expectancy demands on these refractories increase, so do the costs. Materials that improve quality, last longer, are stronger, and require little maintenance are needed for furnaces, ladles, and tundishes.
The steel slabs are glowing cherry red as they leave the mold and head down the runout area. There is careful control of temperature and roller support to ensure the precision of the slab. The high quality of caster slabs makes for better rolling. The process doesn't stop, not even to cut the slabs into manageable lengths. See how the cutting torches are on tracks, synchronized exactly with the speed of the caster? And because slabs vary in metallurgical specifications, each must be numbered so it can be tracked and sent ultimately as sheet steel to a customer. The continuous caster makes better steel slabs than any other method. The caster here at Wheeling Pittsburgh Steel is capable of casting 2.3 million tons of steel a year. Slabs that are more uniform in metallurgy and more uniform and exact in their dimensional specifications. More importantly, think of the caster as a closed loop approach. Because very little air touches the steel as it goes through the caster, there are fewer impurities in the steel. The mold system reduces subsurface defects. The outer surface is cleaner and smoother. It's the kind of steel that puts a smile on the faces of the employees in the rolling mill. We describe the BOF as being a lot like Mom's cake mix. Think of the strip mill as Mom's pie crust. Of course, it's a little more difficult to squeeze a steel slab into a 1/8 inch thick strip than it is to get that apple pie crust just right. Precision and cleanliness are always a concern. Before rolling, we take care to prepare each slab.
A hot mill wants to produce a world-class quality coil.
In order to do that, we must first have a slab that is perfect as possible. Approximately 90% of our slabs accomplish this.
The remaining slabs may need reconditioning by using scarfing torches. This scale drawing shows the phenomenal difference between the slab and the finished coil. It's accomplished by sequential rolling of the steel. The steel slabs are reheated in what looks like a giant oven. Then they start a journey through the 80-inch hot strip mill. The first part of the trip is called the roughing mill. The slabs then enter the coil box. After the coil box, it's delivered to the finishing mill and then sent down to the down coilers. A hot strip coil box processes this 2,000-degree, 1-inch thick transfer bar into a coil form for temperature conservation and equalization. Next, the steel is uncoiled to the finishing mill at an even temperature profile, which helps achieve the temperature and thickness control needed for the customer's order. The coil box helps conserve the reheat furnace fuels and the electrical power requirement. Hot rolling operations such as this must maintain control of the actual work roll temperature, and we do that by water. We apply water with high-pressure sprays, and when I say high-pressure sprays, 200 psi to the rolls to keep the rolls cool in this rolling process. In just 5 roughing stands, the steel is reduced from 9 inches to just under 1 inch. These rolls have to be constantly monitored by inspectors for roll wear. The rolls are periodically resurfaced to ensure an end product of high-quality steel. Within minutes, the rolls are changed and started again. Our roll shop redresses the rolls for the next changeover. The slab travels in a straight line nearly a mile long, squeezed and pushed and shaped every inch of the way. As it gets thinner, it gets longer, and it goes faster and faster until it looks like a blur. And along the way, the coil box, hydraulic AGC, and a very precise computer system work to control temperature, width, and thickness.
The coiler process starts with receiving the strip after it's been produced to the final customer's gauge. It is water quenched, metallurgical specifications are met, and then we coil it. We then inspect it, making sure we provide the quality specification required by the customer. We identify it, which is very critical, and band it for shipment either to our own finishing plants or directly to the customer.
In our finishing plants, Martins Ferry, Ohio, Yorkville, Ohio, Canfield, Ohio, and Allenport, Pennsylvania, making and shipping steel is one measure. Making sure the customer accepts every coil is another measure. And we've been meeting both at Wheeling Pittsburgh Steel. We are large enough to meet rigorous specifications and provide quality steel, yet flexible enough that we can accommodate smaller orders with the same exacting standards. The bottom line is our ability to provide fast turnaround and quick response to all our customers. Hundreds of millions of dollars have been invested in this mill in the past few years because we intend to succeed in the global economy of steel. We hope you've enjoyed this tour of the Steubenville plant as we move toward the 21st century. Advancing technology is certain to change the way steel is made. But one thing new technology cannot improve on is the pride, dedication, and commitment of the thousands of talented people all working together to make a quality product. We intend to continue producing some of the best steel in the world for decades to come. After all, it's our job to make steel happen.